Welcome to today's Research Pays Off. I am going to hand it over to our speaker today, Bill Likos.
Okay, thanks, Lauren. Lauren, can you just confirm that you can see that okay?
Yes, looks great.
All right, good. Well, thank you, Lauren, for the introduction, and thanks for the opportunity to present this work this morning. My name is Bill Likos. I'm faculty at the University of Wisconsin-Madison in the geoengineering group. I'll just take a moment to acknowledge two others who have been involved, who were involved in this work. Tuncer Edel is an emeritus faculty here at UW. He has spent his entire career here working on a lot of projects in transportation infrastructure. He's still very much involved. I'm not sure that he's joined us this morning, but I hope that he has. Hoon-Jun Oh, at the time of this work, was a graduate student in our group. Hoon-Jun is now at the National Renewable Energy Laboratory in Golden, Colorado. So this is a project about drainability of roadway base materials, and what I mean by drainability is gravity drainage. So downward percolation of water through soil or rock or aggregate driven solely by gravity. Drainability is a critical component of really any geosystem, whether that be a roadway base material, such as we're talking about today, or a retaining wall backfill, or an engineered slope. Controlling pore pressures is a critical component of the performance of those systems. One of the objectives of this work was to come up with a way to rate candidate materials qualitatively for drainability, to say that this is a poorly draining material, this is a moderately draining material, this is an excellent draining material, and to do that using relatively simple measurements, things like grain size distribution and porosity. Can we take these relatively simple measurements, screen materials for drainability performance to guide their use in construction? And so that's kind of the direction that we're going here. As I stated, lack of proper pore water drainage is, I think without question, probably the main cause of geosystem failure, regardless of the type of system that is. Some of the things that occur if drainage is not freely draining, or if water is retained in the material, probably the most important is elevated pore pressure and the corresponding decrease in effective stress and the impacts to mechanical properties of soil that depend on effective stress, namely strength and stiffness, compressibility. But also in parts of the world where we have freeze-thaw, if we have water that is retained near the surface and subject to freeze-thaw, that can also cause problems, as we know. With regard to rating materials for drainability, there are a number of empirical and theoretical relations that are available to estimate things like hydraulic conductivity, things like soil water retention from relatively easily measured properties. But like any empirical relationship, these should be used with caution, and really they're only applicable for the data set for which they were developed. And so that is what we tried to do here, is develop a data set for materials specifically that have been used in or have been considered for use in roadway base materials, measure the properties that matter directly, hydraulic conductivity and water retention characteristics, and measure other properties of those materials that are relatively simple to measure, grain size, porosity, for example, and look at correlation between the desired properties and the material properties of the material itself. One of the themes of this project and of this presentation is that drainability is really an unsaturated soil mechanics problem. If we consider this relatively simple schematic down here on the bottom, cross-section for a roadway system, we've got the surface layer, and then this base layer is what we're talking about today. So the compacted engineered base layer, overlying a subgrade. And just for simplicity, I have placed the water table right here at the interface between the base and the subgrade. And I'm showing two profiles to the right there at hydrostatic equilibrium. The first one is the pore water pressure profile, U sub W. And so under hydrostatic equilibrium, pore pressure is 0 at the water table, increases positively and linearly hydrostatically below that water table, and negatively above the water table. We call that matrix suction. You might hear that called capillary pressure. And so that is a water pressure that actually contributes to effective stress. And for some materials, not so much relatively coarse materials like the aggregates that we're looking at today, but for some materials, that increase in effective stress contributes to additional strength and stiffness of the system. The other curve on the far right, we call the saltwater characteristic curve, or SWCC, and that is quantifying the amount of water in terms of degree of saturation that is retained by that material under hydrostatic equilibrium conditions. And so you can see down near the water table, that material, depending on grain size, can still be saturated up to some finite distance above the water table. We might call that the capillary fringe. That point where the degree of saturation starts to decrease as we get higher above the water table, and we're experiencing higher suction pressures. We call that the air entry pressure. And so the degree of saturation starts to decrease there. And then the shape of that curve is related to primarily pore size distribution, which is indirectly related to grain size distribution. Materials that have a high air entry pressure are generally fine grained. They'll remain saturated at relatively high suction pressures. So when water is added to the system, let's say it rains or we have a snow melt event or something like that, and water gets into the base, both of those profiles are going to shift to the right. We're going to have increases in pore pressure from negative values to less negative values, perhaps even positive values temporarily if we have ponding at the surface. And the saturation profile will also shift toward higher saturations, and that pulse of water will drain through that system and eventually reach hydrostatic equilibrium again. And so that's the drainability process. That's the gravity-driven drainage that we're talking about here. Going back to the top of the slide there are three things that really govern this process, two of which we have control over and one of which we don't have much control over. The two that we have control over are the material properties of the base. This is material that we have selected to have desirable both drainability and strength characteristics, and that the drainability characteristics that matter are the permeability and the water retention characteristics. And so saturated hydraulic conductivity and the water retention characteristics which produce the soil water characteristic curve over there on the right. We also have control over the design of the system itself, the various layering, any slope at the surface, any natural or engineered drainage boundaries. Those are also going to play a role in not just how much water is delivered to the system in the first place, but how it can be diverted, for example, without penetrating into the base. And then the one that we don't have much control over, environmental conditions. How much does it rain? What's the relative humidity and temperature that draw water back out of the system? So this project is about the first of those three, the material properties. How can we screen materials to have desirable drainability characteristics during design phase? So the objectives of this project, this is a primarily laboratory based project where we conducted permeability and water retention tests on materials submitted by NRRA stakeholders, MnDOT, MoDOT, and Wisconsin DOT that have been used in or are being considered used in pavement-based systems. We directly measured saturated hydraulic conductivity and soil water characteristic curves for these materials, and then explored simple tools that can be used to estimate those two properties from relatively simple measurements like gradation, fines content, and then took that information to develop a qualitative rating system where we could say, all right, if I have the grain size distribution for this curve, can I use that information to say that this is a poorly grading material, a well draining material, or an excellent draining material? So these are the materials that we obtained as part of this project. 16 in total. You'll see in a moment that about half of these are classified as sandy materials. About half of them are classified as gravelly materials. To give you a sense of what these look like, here are the first four on that table there, and corresponding soil classification. So number one there is a poorly graded sand, silty sand, and number four down there is a silty gravel. So we're talking about a pretty wide range of grain sizes with these materials. If we look at particle size distributions from sieve analysis for these materials, again, you can see the pretty wide range of materials ranging all the way from poorly graded gravel size materials there on the left side to materials that have some significant fines content. That vertical line there is dividing coarse grain and fine grain by size. And you can see that the fines content for these materials ranges basically from 0 to about 20%. So we have a pretty good, a pretty wide representation of materials to test here, which is desirable from if we're going to be developing empirical correlations from this data set. There's a lot of information on this table here, but I just wanted to summarize some of the things that we were able to quantify for each one. So the various particle size indexes there on the left, percent fines, there it is, ranging from about 0 to 23%, percent gravel, and then coefficients of uniformity and curvature that we will use later, as you'll see, in developing some of these correlations. And then corresponding soil classifications for each of those 16 materials. Again, about 9 sandy materials and 7 gravelly materials. So a nice wide range. As I mentioned, we measured saturated hydraulic conductivity and water retention curves. These are photos of the experimental systems that we used to do that. So the one on the left is a rigid-walled constant head apparatus where we compacted these materials at optimum, or as close to optimum as we could get, within 95%. That permeameter, I recall, is about 6 inches tall and 4 inches in diameter, so relatively large to capture these larger grain systems. This is a constant head apparatus, and so you'll see a reservoir there on the right and a reservoir on the left that we use to control the hydraulic gradient to flush water from bottom to top through the specimen, measure the outflow rate, and then calculate hydraulic conductivity. One of the features of this permeameter, you'll notice the tubing there is really quite large. We used large tubing and low head loss connections and elbows and things like that to minimize as best we could head losses that are attributable to flow through the system itself, as opposed to flow through the material. If there's relatively low head loss through the material, which there is in these coarse grain systems, we want to minimize head losses through the system itself, so that we don't include those as in the conductivity calculation. The apparatus on the right there is a hanging column apparatus. There are a number of ways to measure soil water characteristic curves. Most of them are applicable over relatively limited ranges of suction. And so for these materials, the hanging column apparatus is the appropriate system to use for these relatively low suctions that we're applying, less than 5 to 10 kPa. We could probably go up to about 100 kPa with a system like this. The way that it works, we've got the specimen sitting in a cylindrical sample holder there on the right. Again, that's a large diameter cell. If I remember, that was about 12 inches in diameter to be representative of the grain size here. There's a ceramic disc on the bottom of that cell that separates the soil from the system with which we apply suction pressure. So we're applying negative water pressure to the bottom of that through the ceramic disc and pulling water out of the material at a controlled suction. We control suction by manipulating the relative height of these two reservoirs on the left. And so if that one on the far left is lowered relative to the static one at the top, we're essentially pulling on the bottom of that reservoir with a column of water, producing a negative air pressure, the green portion there. That the horizontal tube coming out of the bottom of the cell has an air-water interface in it that when we pull that negative air pressure, we're converting that to a negative water pressure and pulling it out of the soil. And we can measure the volume of moisture or the volume of water that we are extracting from the soil by monitoring the movement of that air-water interface. Here are some results from hydraulic conductivity testing first, and then we'll look at some results from the soil water characteristic curve testing. This figure separates the 16 materials into the sandy materials there on the left and the gravelly materials on the right. And what we're looking at is saturated hydraulic conductivity as a function of hydraulic gradient. We applied hydraulic gradients ranging from 0.25 to 2 to be representative of typical base applications. And you can see for the sands, there's not really much sensitivity of hydraulic conductivity to the applied gradient. For the gravels, we saw a general, at least for some materials, decrease in hydraulic conductivity with increasing gradient, which is likely due to fines migration. We may be mobilizing fines at those higher gradients through the system that can get hung up at in particular pore throats and reduce the hydraulic conductivity. For the really open graded materials, that may be related to turbulent flow that develops at higher gradients. And so that's an observation that we had, and for subsequent calculations, we took the average. So those vertical or those horizontal lines through there are averages across the range of gradients. So those are our hydraulic conductivity measurements. Here are our soil water characteristic curves. And so again, broken up into the sandy materials on the left and the gravelly materials on the right. If you go back to that image that we looked at on one of the first slides, these are essentially those curves. I mean, if you replace the vertical axis there, you could convert that directly to a height above a water table. And we're looking at volumetric water content, the relationship between volumetric water content and suction. You could convert that to degree of saturation on the horizontal axis and height above the water table on the vertical axis. The equation there on the bottom is the Van Gunukten model. And so that's what those continuous lines are through the data points. The data points are direct measurements where we had applied increments of suction through the hanging column apparatus, measured corresponding water content, creating a discrete set of data points to model those continuously. The Van Gunukten model is a very commonly used model for the soil water characteristic curve. There are two parameters that I want to point out in that model. So the equation down there in the bottom, alpha and n, are fitting parameters that we optimize to provide the best fit to the experimental data. When we start looking at, correlating things like grain size or porosity to predict soil water characteristic curves, what we're going to be doing is correlating grain size to things like the alpha parameter. Can we predict alpha from grain size, for example? Can we predict N from grain size? If we can do that in a reasonable way, then we can use grain size to model saltwater characteristic curves. Again, this table has lots of information, so I'll just kind of point out a few things. So these are for the 16 samples. Here are densities that are dry densities that are dry unit weights that these were compacted to. Minimum saturation, so that is likely at the highest gradient applied, and then maximum. And there's the average saturated hydraulic conductivity. And so those are those dashed lines through the data that we were looking at before. The standard deviation gives us a sense of the difference between the minimum and the maximum. And so you can see for the gravels, like number 4 and number 9 here, larger standard deviations are indicating sensitivity to the applied hydraulic gradient. The average conductivity for the gravels was about 0.3 centimeters per second, and for the sand about 0.015, so within expected ranges. The information on the right there are those Van Gunupten saltwater characteristic curve parameters for each of the materials. And so this becomes the data set that we can develop correlations to things like grain size from. I wanted to point out another important parameter here, or series of parameters, and that is what we might call field capacity, drainable porosity, and minimum saturation. Field capacity is defined as the volumetric water content at gravity drainage. Okay, so we imagine a column of material that we saturate and allow permeation from the base. That's going to have some moisture content after drainage is complete. The higher that value is, the higher the field capacity for that material. Drainable porosity, or you might see this called effective porosity, is the porosity of the material minus that water content at field capacity. And then minimum saturation is the saturation corresponding to field capacity. Field capacity is typically defined at a matrix suction of 33 kPa. And so that's this horizontal line here running through some of these saltwater characteristic curves. And so you can see that the material with the blue triangles over here on the far right, the degree of saturation at field capacity is about 50% or so. Not effective drainage of that material by gravity. So that would be would be what we define as the minimum saturation for that material, about 50%. You can see that on the far left there, that is a very well draining material, minimum saturation, some value less than a few percent. Here is a table of total porosity, field capacity, drainable porosity, and minimum saturation for each of the materials that we were able to determine from the measured saltwater characteristic curves. And what I'm showing is the relationship between percent fines and the minimum saturation. So it's not surprising that as the percent fines increase, we have greater retention in that material. So we see a pretty reasonable correlation between minimum saturation and percent fines. This is a correlation that we'll come back to later as a mechanism to rate the drainability of materials based on a relatively simple measurement of percent fines. This is another example of a correlation that we explored between saturated hydraulic conductivity and grain size parameter D30, so the grain size corresponding to 30% finer material. This is a plot of the data set down here on the left. So there's D30 and the average saturated hydraulic conductivity. This is one of the more robust correlations that we saw. There's the equation for it up there. On the plot on the right is a comparison between measured saturated hydraulic conductivity and a value that we would estimate using that correlation. So the bold line running diagonal is a perfect correlation, and then the two dashed lines are within 10% and 20%. And so you can see that this correlation for this data set of materials, for the entire data set, is within 20%, and for the majority of materials, that prediction is within 10%. So D30, at least for this group of materials, is a pretty satisfactory, relatively easily measured property for correlation to saturated hydraulic conductivity. To predict empirically those saltwater characteristic curve parameters, we explored an approach that was published by Benson et al. Using sandy materials, relatively poorly graded sandy materials, which are a little bit different than this data set, but we can use the same basic approach for this specific data set. And so the way that this works, what we're after doing is predicting those two Van Ganupten parameters that I pointed out earlier, alpha and n. The equations there, the first is a correlation between alpha and D30, as well as coefficient of uniformity. And then we can predict n from D30 and coefficient of uniformity. So those are equations specific for this data set. The two figures on the bottom show the performance, which is reasonable for n. You can see that most of those predictions there are within 10, maybe 15%. And for the alpha parameter is reasonable for alpha values below about 0.5, which is within the range that we would be most interested in for drainability of base materials. You know, an alpha value of about 0.5 corresponds to an air entry pressure of 2 kPa. Most of those materials are going to be reaching air entry pressure around or below that value. With regard to the drainability rating system, so again, the idea here is to say, can we use saturated hydraulic conductivity and minimum saturation to qualify a material as an excellent draining material, marginal draining material, or poorly draining material? To do that, we need to set bounds on both saturated hydraulic conductivity and minimum saturation, which is the other parameter that we chose for this rating system, because minimum saturation captures the saltwater characteristic curve. We identified or set a boundary for excellent in terms of saturated hydraulic conductivity greater than 0.3 centimeters per second. That is based on FHW and FHWA definition of an excellent draining material. Whereas FHWA would define a relatively impermeable material as one with the saturation or saturated hydraulic conductivity less than 0.02 centimeters per second. And so that's what we set as our lower boundary, and then marginal for the range between those two. The minimum saturation we said if it's less than 0.1, in other words, if that soil at gravity drainage is holding less than 10% water by saturation, we would consider that an excellent material, and poor if that is greater than 30%. So now we have three approaches. If this is our qualitative rating system, we've got to determine Ksat and minimum saturation. So we propose three ways to do that. One is to directly measure those two, as we did in this study. Two is to estimate them from grain size using the correlations that we developed in this study. And the third approach would be to estimate them simply from percent fines. And so we'll look at how these different materials are rated using these three approaches here. If we look at direct measurements, here are the 16 materials. The next two columns are the directly measured saturated conductivity and the directly measured minimum saturation. If we apply those bounds to the conductivity criterion, the first material there would be rated as poor. That conductivity is very low, and its minimum saturation would be rated as marginal. So we would combine those two criteria to give an overall rating. Let's call that one poor to marginal. The two that are highlighted there, number 6, you can see an image of it over there on the right, meets the criteria as excellent in both categories, and so overall we would qualify that as an excellent draining material. By comparison, If you look at number 15, which is classified as a silty gravel, rates poorly with regard to both of those criteria and poor overall. So it would take direct measurements of both the hydraulic conductivity function, or the saturated hydraulic conductivity, and the saltwater characteristic curve to develop this table, which is not often done. Hydraulic conductivity may or may not be measured. Saltwater characteristic curves, I would say, would be rarely measured in practice. They take a lot of time and expertise, and so there's motivation to explore these empirical relations. The first of which, if we say, okay, let's just use grain size. Let's measure by sieve analysis the grain size distribution of this material, estimate saturated hydraulic conductivity using D30, as you can see in that box up on there on the top. Estimate the two Van Ganukten parameters using D30 and coefficient of uniformity to predict the minimum saturation. We would predict minimum saturation by plugging in 33 kPa as our suction value. That defines, again, our field capacity. If we run the numbers through this system for each of those materials, these are the results that we get. And so just highlighting those two from before, number 6 and number 15, again, we have an excellent draining material and a poorly draining material. In a future slide, we'll look at comparisons between direct measurements and this indirect estimation approach. Our third approach would be simply percent fines. And so again, using sieve analysis to calculate or to measure percent fines. There is that correlation that we saw between minimum saturation and percent fines. If we establish those two rating bounds on this curve, on this plot down here, where we've got a hydraulic conductivity greater than 0.02 and a minimum saturation less than 0.3, those red triangles are where the percent fines fall within those bounds. And so that allows us, so anything falling in that yellow square down there has a relatively high hydraulic conductivity, relatively low minimum saturation. Those would be classified as excellent draining materials. Anything in the blue box would be a marginal, and anything out in the white portion would be classified as a poorly draining material. So again, if you compare those two that we were looking at before, number 6 and number 15, we've got consistent ratings using percent fines alone. If we compare all three, and so the three columns here now are ratings based on direct measurement, ratings based on grain size, and ratings based on percent fines. We see fairly consistent classifications according to the three. If anything, the estimate from percent fines is a little bit conservative. In other words, we would rate a material as more poorly draining than direct measurement. And if anything, the estimates from grain size are a little bit, I'll say optimistic. We would get a more excellent or a few more marginals in that column. But overall, consistent correlation between direct measurements and these relatively simple estimation approaches. And so that's what we're trying to bring here. For this specific data set, for materials that can be used or have been used in roadway-based construction, can we screen them for drainability in using relatively simple measurements? So to summarize, what did we do? We measured saturated hydraulic conductivity. We saw that the values of saturated conductivity for sandy materials were independent of hydraulic gradient. Well, there's those for gravels. We saw a slight decrease in conductivity with increasing gradient, probably attributable to migration of fines and potentially turbulent flow. Not surprisingly, we saw that saturated conductivity generally increases as grain size increases, or as percent fines and our unit weight decrease. In other words, if we've got less fines or a higher porosity material. We saw that KSAT was reasonably estimated from grain size, particularly D10. We didn't look at D10 in this presentation, but that one was also reasonable. The D30, at least for this data set, was the most robust correlation. In terms of predicting saltwater characteristic curve parameters N and alpha, we saw that we could estimate the N value, which governs kind of the shape of that characteristic curve related to pore size distribution. We could reasonably estimate that within 10% from grain size, and we could reasonably estimate alpha for alpha values less than about 0.6, which is about within the range where we would be for a base material. And then finally, we developed a rating system for qualitative assessment of these materials using any of three approaches: direct measurement of the properties that we think matter, saturated conductivity and minimum saturation, indirect estimation of those from grain size, and then indirectly from percent fines. And then, as we noted on that last slide, drainability is perhaps optimistically related when we use grain size and conservatively rated when we use percent fines. And then finally, and I'll be happy to answer questions, there are a few publications that you can refer to from this work. The first is the NRRA report that was published in 2021. And then there was a subsequent paper in Transportation Research Record published in 2022. I believe the NRRA report is available on the website. You can find that relatively quickly. And this one, if you'd like a copy, I'd be happy to send it to you, or if you can't find it online, please let me know and I'd be happy to share it. So with that, I will conclude and be happy to answer any questions. Thank you.
Thank you so much. I know we have had a couple comments in the chat. So let me go through that. A little bit ago, Bernard asked what assumptions or idealizations are in the Van Geneuchten model.
Yeah, the Van Geneuchten model, which is the equation down there on the bottom, is simply a curve fitting model. It is we optimize those parameters. We get a spreadsheet to select alpha and N to best fit the experimental data. So it is entirely a curve fitting model. It's not theoretically based. There are relations between these parameters. I mentioned N, for example, is related to the shape of that characteristic curve. A certain value of N will produce a relatively flat curve. A certain value of N will produce a relatively steep curve. And so N is loosely tied to pore size distribution. Alpha is loosely tied to air entry pressure. So there is some physical relation to the parameters, but no theoretical basis. It's a curve fitting model.
Lauren, you're muted.
Thank you. Then our other question here is from Raghu. Have you done any comparisons based on different material sources like limestone versus granite rock materials? Or do you think the same correlations are applicable, including degree of saturation and suction?
That's a good question. We didn't look at aggregate type specifically, although I'll have to go back. I do think we have a pretty wide range of aggregate source or aggregate mineralogy. I don't think that it would impact either saturated hydraulic conductivity or saltwater retention curves significantly. I mean, these are governed by grain size distribution, pore size distribution, porosity. There may be some effects at relatively high suctions, so way up here on the curves, but at these very high suctions, we're talking about interaction between the water and the mineral surfaces. where mineralogy does play a more important role. But the size of these materials and the size of the pores that we're dealing with, this is about water that's in the larger pores. It's not about that surface absorbed water. And so I would be very surprised to see any effect of let's say granite versus limestone in terms of what we're looking at here.
Okay. Oh, and it looks like I was just gonna call in Supraja because I know she had her hand up. Supraja, did you want to mention
Hi.
anything else?
Yeah, I just
I just
typed
saw your
in.
comment,
I
but
realized maybe I should type in. Anyway, I can talk now. So the percent finds method. Thank you again for the great presentation. A lot of information. Nice one. We can use it in the field. Um, uh, so when we use percent find methods to correlate, um, should we use it in conjunction with the Utterberg limits, or it is assumed that it it is certain Utterberg limits that go along with percent fines?
Yeah, so we didn't measure Atterberg limits. We simply measured percent fines from sieve analysis. It's a really good thought, though. I wouldn't be surprised if there is some normalization that could be done. For example, I mean, a high plasticity percent, percent fines that contain a high plasticity clay are going to retain more water than the same percent fines of a lower plasticity clay. We didn't look at that, but that would definitely be a way to refine this correlation. That's an excellent thought.
Thank you. Thank you.
all right. And then our other question came from Deepak. How do you relate to degree of compaction?
Yeah, so degree of compaction. So again, for this data set, we wanted to simulate field compaction. And so we compacted all of the materials for both the hydraulic conductivity measurements and the soil water characteristic curve measurements. We compacted them to within 95%. I believe it was standard Proctor. Certainly compaction is going to have an effect. Compaction is going to affect both hydraulic conductivity and water retention. But the presumption is that these materials, the drainability problem that we're interested in is going to be the compacted state in the field. So we wanted to bring the conductivity measurements and water retention curve measurements to those values.
Okay, and then the last thing I see here in the chat is from Jay. He says, hey, Bill, nice presentation. Any thoughts on how this would correlate to recycled materials like crushed concrete or wrap?
Yeah, that's a good question. I can't remember. I don't know that we had recycled materials in this. I don't think we did. Again, I mean, I think this is similar to the discussion we had earlier about, granite versus limestone. I mean, I think, again, the properties that matter are pore size distribution, compaction, as we just discussed. So hydraulic conductivity and water retention curves are going to be governed less by surface interactions than by pore characteristics. RAP is a little bit of a different animal. I mean, RAP has some interesting hydraulic conductivity and infiltration behavior. That one may or may not be applicable to this data set.
And I thank you. I saw Raul raise his hand, but put it back down. Did you want to say
I
something?
did. Yes, I did. Thank you, Bill, for the presentation. I just want your thoughts about, are we being conservative or not conservative when we don't take into account the framework of unsaturated soil mechanics? As a practitioner, we tend to focus too much just on moisture on one aspect of that soil water characteristic curve, but we don't talk about the energy state of the water, the suction. And what are your thoughts on, should we spend more time ourselves investing on that, thinking about the drainage with that framework, with unsaturated framework? Are we doing, conservative or unconservative? I want to get your thoughts on it.
Well, I certainly think we should be. I mean, I've spent most of my time dealing with unsaturated soil mechanics, and I am constantly trying to find ways to integrate unsaturated soil mechanics into practice. That was really what drove this project. You know, let's recognize that drainability, the soil water retention curve matters, yet it's difficult to measure, and for that reason, very rarely measured. Can we lower the bar a little bit? Can we say, all right, well, let's try and indirectly integrate unsaturated soil mechanics by doing things that we're already doing, like measuring grain size, for example. So yes, I think, Raul, we need to be integrating unsaturated soil mechanics into practice. It is what's governing the behavior of the system. We're only talking about drainage here today, but I would argue strength and compressibility are equally as important. I think we are being conservative, particularly in aspects of strength and compressibility, when we don't account for effective stresses that are induced by negative pressures. We just do a better job, I think, by recognizing the state of the soil. If it's partially saturated, let's do what we can to recognize that and take advantage of the desirable aspects of behavior that result from that.
Thank you, Bill, very much.
Thank you.
Any other questions or comments? Gone through everything that was in the chat. So if anyone has anything else, feel free to speak up. Otherwise, we can wrap a few minutes early here today. All right. Well, Bill, if you're okay with it, you can certainly send your presentation to me, and I can upload it to the website as well to give people access to it, or people can contact you directly. Do you have a
I'd be happy
preference?
to share it with you, and I'd be happy
Okay.
to take any direct contact. You can find my contact information. Maybe Lauren, I don't know if you sent it out with the invitation, but it's there. If not, you can find it on the UW-Madison Civil Engineering Department website. Let me just say thanks to everybody for joining, and thank you for the excellent questions. I really appreciate the opportunity to present this.